This video looks at the TCPDump program from Linux. This is a very useful packet capture program that comes included with most Linux distributions, and it's included on the Backtrack 5 that we're using in the demo. So the basic network that we have is a VirtualBox network. So we have a Windows XP machine running, and we have a Backtrack 5 machine running, and we'll set up some communication between those two machines to give us some traffic that we can capture and analyze. So the first thing we're going to do is we're going to approach this as if we don't know which machines are on the network. We are going to restrict ourselves to the virtual network so that we can avoid the private network that the laptop happens to be running on. So we're going to use nmap to scan the network to find the different machines. We're going to use some different options. We're going to use the -O option, which will help us do operating system discovery. -SV will probe the different services that are running on the different ports that are found, and the service probes contain expressions in the services file that can be matched against the responses to help nmap figure out what's running on that port. So for example, with this option, nmap cannot just guess that FTP might be running on a port 21, but it can actually send a small probe to that port 21, look at the response, and match that response against the responses in its services file. If it gets a match, you can actually, with high predictability, tell the brand of the service running, the type of service running, and sometimes even the version of the service running. So we also have the -V option, which is a verbose output. We're going to use --reason because we want nmap to tell us why it thinks that a certain port is open. --open flag tells nmap to only tell us about open ports. With the type of output that we're going to be using, if you don't use the open flag, you'll get information about all the ports scanned, and it can make the report a little bit noisy. We're going to output this to an XML file using the nmap XML format. This format is not only nice to read inside of a web browser, but it also is very transferable. You can load it into Metasploit Community Edition, regular Metasploit using the db import command, and other tools like Dradis. So we're just going to save this as an nmap scan of, let's call it 192.168.50.0.nmap.xml. We're also going to have a style sheet recorded into this XML file, so that web browsers that are looking at the XML file can translate it into HTML and display some nice output. Otherwise, the web browser is literally just going to display the XML, and that's not going to give us a very good graphical picture of the network. What we want is we want a nice formatted output. There's an XSL file that comes with nmap that does a nice job of this, and we can include it just by using the style sheet flag and then giving the port, or the path, to the style sheet, and it's found in user local share nmap. Do a double tab and we can see that the file is there. So we could say nmap.xsl. We're not actually going to hard code it into the file like that, because if we were to export this XML file to another machine, or a machine like Windows that doesn't even have that directory in it, it's not going to be able to find this file. Plus, if we transport it to another machine that doesn't even have nmap period, then that machine is not going to have the nmap.xsl file that's installed with nmap. So instead, what we're going to do is we're going to just hard code the XSL to be local, which means that wherever this XML file is transported to, we have to make certain that there's a copy of the XSL file with it. Otherwise, the style sheet will be missing and the output won't display properly in the browser. Now for importing the XML file into tools like Metasploit, the XSL file serves no purpose at all. It's only used when formatting the XML into HTML within a web browser. So we have the basic commands for nmap to scan this network and to output to the nmap.xml file. We could use other options, but these options should do nicely. We're going to go ahead and let nmap start running. And one mistake I made is I never actually said what network to scan. So we're going to do 192.168.50/24, and that'll scan the entire 56.0 subnet. An alternative way to do this would have been to say 0 through 255. It's basically equivalent, but the sitter notation is more generally used and is more prevalent nowadays with classless networks. And let's see if nmap likes it a little bit better when I actually tell it what IP address range to scan. And it looks like it's off to a good start. And while this nmap scan is running, we can take a real quick look at the services file. User local share nmap. And there's the nmap services and service probes. So services is the mappings for the ports. So in other words, it's saying that like port 21 is FTP, for example. Now the service probes file is the one that sends the probes and then listens for the response and compares the response against the probes in the file. So for example, there would be a probe that gets sent out. This one's a really simple one. It's just a TCP null, and then it looks for a match on, for example, this pattern here. And if it figures out that pattern, then it says, well, that's the active sync service. Let's go back to our scan, and it looks like the scan is done. The default nmap output is pretty good. You can certainly tell that there's a web server running on 102, and it's probably a Windows box because it's got 139 open, TCP, and which is Samba over NetBIOS. So we can also see that the services probe found the Apache running on this box down here, and it found that 139 was NetBIOS. And then the -O option gave us the Microsoft Windows XP SP3, and that means that it matched some of the responses back from the machine against some patterns and believes that those patterns match the Windows XP SP3. And it turns out it's right. That is the machine that is running at 102. So now that we have the output, we have the nmap file that's in XML format, and we've already copied nmap.xsl to this directory. So now nmap.xsl is right next to the XML file. And the reason this is important is that when the Firefox opens that XML file, it needs to be able to find that nmap.xsl. And recall that we had specified that it was going to be in the local directory. And we can take a closer look at the XML file to get a better understanding. So we can see right here the href to the nmap.xsl file is exactly like we told it to be hard-coded. It's just nmap.xsl. If we had put some path in the style sheet, it would be hard-coded here. Now the browser knows where to find the XSL file. So do a Firefox XML file. We'll use the ampersand option so that Firefox runs as a background job and doesn't steal our terminal prompt here. And here's our file formatted with the style sheet. So we can see that it found a box at 56.1, and that box is probably Windows because port 3389, which is the remote desktop port typically, and nmap is about 91% confident that it is a Windows box, and it's true, it is. It turns out to be Windows 7. And we have address 101, which has port 111 open, which means it's probably a Linux box, and it is. It's the one that we're using here. And then we have box 102, which we already said nmap believes is a Windows XP SP3, which is 100% confidence, and it turns out that that is true. And there's a web server running on this 102. We're going to use that as our capture for our TCPDump. WebTraffic makes a nice demo for TCPDump because it has several network layers in it. You have your IP and TCP packets, but then you also have these HTTP inside of the TCP packets, which can be taken apart with other tools, so we can sort of look at each layer of the protocol together. So we'll go ahead and take a look at the TCPDump a little bit closer and work our way up to capturing some packets for that HTTP traffic. So TCPDump-D will show the interfaces on this machine that TCPDump can capture from. And there's ETH1 and ETH2 plus the NA pseudo device, which it just captures from all of the interfaces at once. That can get quite noisy without filters. And LO is the local host. So we're going to go ahead and take a look with ifconfig to figure out the difference between ETH1 and ETH2. So ETH1 is capturing on that VirtualBox network because it has the 56 subnet in it. And then ETH2 is capturing on this private network that the laptop also happens to be connected to. And the route command shows that the .1 network is the one that goes out to the internet. The default gateway is the .1 network. And the 56, we know that it happens to be the VirtualBox network, but that's another indication that it's a local private network and not the one connected out to the internet is the default gateway. It turns out VirtualBox by default always uses the 56 subnet. You can change that in the settings if you want, and that's found over here in the file preferences. And you go over to the DHCP server, and when you get into there, you can set what that subnet is, and you can also set what the starting address is going to be. You go to network, and there's this host only Ethernet adapter, and we can see that the network address is that 56 subnet with the net mask, allowing only the last octet to change. And we can see the DHCP server starts at 100 and goes up from there. So the first one given out is 101, which happens to be our Linux box, which makes sense because we started the Linux box first, and then we started the Windows box second, so it happened to get the 102. So it kind of makes sense how all these IP addresses actually happened if we have all this knowledge of the network. Naturally, we're using nmap to approach this demo as if we didn't really know any of that, and so we can actually discover the machines and figure out what ports are running on and so forth. So back to TCPDump. So we know that we're going to capture on interface, which is -I, ETH1, because we want to look at the traffic between us and the Windows box, which is on the 56 network, and that's what ETH1 is listening to. Some other options we're going to use is -X. Now -x will display the hex output of the packets captured, which is nice visually. -A, capital A, will display the ASCII, but -X will display both the hex and the ASCII. We're also going to do a -NN. So the first N says, instead of displaying the host names of host, display the IP address. And the second N says, instead of displaying the port name, like FTP for example, display the port number, like 21 for example. We're going to use verbose output, which is -V, and then you can add a second to get a little more information, and then add a third to get the maximum amount of information. Next is snap length. This setting is important. Sometimes it's a little bit confusing, but essentially the snap length is the number of bytes of each packet to capture. So if we set snap length of 1,000, then the first 1,000 bytes of each packet will be captured. And that may or may not be the entire packet. It depends on if the packet fits in 1,000 bytes. Well, we can do a snap length of 0, and 0 essentially means that we're not going to limit how many bytes are captured, or it's kind of equivalent to saying a snap length of 65,535, since that's supposed to be the maximum size of the packets. Of course, the machine can send a packet of any size at once, but that's supposed to be the limit. And we're also going to look at some other options here in a minute of how to write the files out and how to restrict the hosts. But for now, we're just going to leave these options just to get a quick look at how TCPDump captures traffic. So it's listening on ETH1 to anything that comes across that wire. We can do it. Ping 192.168.56.103. And we can see that a ping was sent out. The first packet is an ARP, address resolution protocol packet, sent out, and it's asking who has 103. That's the machine that we pinged, and we want to tell us 101. And there wasn't actually any responses coming back. Machine 103 doesn't actually exist. We only found 101 and 102 when we did our network sweep with nmap. So it kind of makes sense that nothing came back. So we're going to stop listening for a second. And why don't we go ahead and set up a ping at 102. Go ahead and start capturing. And notice that when we start capturing, it tells us that we're listening on ETH1. That was specified with the -I option. And then also that our capture size is 65,535 bytes, which was specified with the -S0 option. We'll do the ping, let a couple of packets fly, and now we get a lot more traffic. So this time we have an ARP of who is 102, tell us 101, and we actually got a reply this time. 102 is this MAC address here. This being a virtual network, we can set the MAC addresses to whatever we want, but this is the MAC that was given out by the virtual box to 102. And then we see the ping packet, and the way to read this is IP address 101 sent, that's the arrow pointing to the right, a packet to machine 102, and that type from the dash, which is displayed because of the dash verbose, is an ICMP echo request with an ID of 37941, sequence 1, and length was 64, and so on. This information here that's being displayed by TCPDump is the hex of the packet sent, and over here is the equivalent ASCII of that hex, and that was caused by the -X option. So we can get an idea of how TCPDump works, and we can improve on it a little bit. One of the things we can try to do is restrict what packets that we actually see, and to do that there's several commands we can use. For example, we can only capture ARP traffic by just saying ARP, or we can capture ARPs and UDPs by saying ARP and UDP. Fairly simple for the protocols. There's also a host directive, so we can say only capture traffic going to and from 192.168.56.101. That's us. So we would only get packets going either from our machine to another machine or to our machine. We could be even more restrictive and say the source is 192.168.56.101, or we could, and the destination is 192.168.56.102, the other machine. But then we would only get the packets going in one direction. So we could add the OR operator, and we could say 192.168.56.102 is the source, and 192.168.56.101 is the destination. But we need to group these together. So we would have to say the source is us and the destination is the web server, or the source is the web server and the destination is us. But these brackets are special characters, so if we hit this, we're going to get bash complaining because those brackets mean something to bash, and so we need to escape the brackets. We can fix that. Let's go ahead and clear the screen so we can see it better. We can fix that by just putting the entire packet filtering syntax in single quotes. And so now we've got TCPDump listening again. Another way to do that would have been to escape those brackets with the slash beforehand. That would tell bash to take the brackets literally, like don't try to use them as a command. But it seems a little easier and more clear to put everything in quotes. To each his own. So we'll do the ping again to 192.168.56.103, the machine that didn't exist. Notice we didn't capture any traffic because we had gotten those ARPs before, but we're not getting them now since 103 is not in the filter. And then we'll just go ahead and do 102. And we did capture the traffic because it's in the filter. So we have the echo request going out and then we have the echo reply coming back. So again, the way to read this is 101 sent a packet to 102, and then 102 sent a packet back to 101. Perhaps that's from our point of view, but that's how the packets work. So the next item on TCPDump is to go ahead and start to capture some traffic that is a little more complicated. In this case, we're going to use the web traffic from machine 102, or to 102 as well. We can go ahead and get some traffic going to machine 102 by using netcat or port 80, and we'll just do a GET request for the root directory. We're going to use the HTTP 1.1 protocol, and we have to include the host header because HTTP 1.1 requires a host header or else it's an error. And then hit enter 2 times. And that tells the response coming back from the server tells us that it's a redirection, a 302 redirect to location 102 XAMPP. So the way that this web server is set up is it doesn't serve any content out of its root, it serves content by default out of this XAMPP directory, and it's redirecting us to that directory. We can go ahead and take a look at that. and the output returns from the web server. So now we can start TCPDump listening and recreate those events. Okay, we're going to enter twice to send the traffic. The traffic returns with a web page, and we've captured those packets in TCPDump. If we scroll up a little bit, we can see the actual traffic. There's the span, the href, and if we look over here, we can see the equivalent right here. So this packet started off with the H2 field, which is about right there, and the response we got. So the packets have been captured along with their inner protocols. And that's pretty useful, but the captured traffic is just on the screen and we can't do much with it. So this time what we're going to do is we're going to add the write command, which is -w for write, and then the name of the file we want to write to. So we're going to call it packets.pcap, and pcap extension is because it's a pcap output file, that's the format. We'll just recreate the traffic again. And it says I got 12 packets. So what we can do is we can read the file back in with TCPDump. You can read pcap files, -r for read, and it'll replay what was captured. But another way to look at the captured packets graphically would be to use Wireshark. So we'll do a Wireshark and then the name of the file. Ampersand to run it as a background job, so Wireshark doesn't steal our terminal command line until we turn Wireshark off. And here's the packet capture file opened up in Wireshark. So there's the get. We can look at it a little bit closer. And there's the actual get statement with the host header, and then the /ends is the two carriage returns we did by hitting the enter key twice. We can right click on that line, say follow TCP stream, to have Wireshark reassemble all the packets that are part of that stream. The red is the request going from 101 to 102 from us to the web server, and then the blue is the response from the web server. We can actually take this HTML, this higher level protocol that we captured inside the packets, and we can play it in the web browser to see what it looked like. It's not a very complicated page. It's basically just saying that we don't have access to the site, but just for demonstration purposes, it's interesting to look at the file played back in the browser. Okay, save that file. After pasting it, the program used was gedit, a nice WordPad-like program that comes with Linux. Actually, it's quite a bit better than WordPad, but that's probably the closest example to Windows without actually getting third-party software like Programmer's Notepad 2. And then we'll open that up in Firefox. here is the HTML that we captured played back. It looks like we grabbed a few more packets than we probably should have when we scraped the screen, but it's pretty close. So we've essentially reconstructed the entire packet capture back into its HTML content, all the way from IP to TCP to looking at everything in Wireshark, reassembling the packets in Wireshark, and then playing them back in the Firefox web browser. Now there's another web server running that we can do to make this demo more real world and put together an end-to-end capture. So go ahead and clear the screens. And we'll start TCPDump listening. And we're just going to use a normal browser to browse to one of the web servers running on that box. Excuse me, one of the websites. Matilde. This site's realistic and it'll give us a good example of what real traffic looks like. So we got 561 packets, now 573, as Matilde finishes loading its home page. We'll stop TCPDump, and then we'll go ahead and look at the packets captured in Wireshark. Now we have the GET that was issued by the Firefox web browser, which is analogous to us using Netcat to do the same earlier. We're going to right click and say follow TCP stream, and we can see the much better formatted, or perhaps a better way to put it is the less lazy request sent to Matilde by the Firefox web browser, and then in blue is the response coming back from 102. And we can put this back together by capturing from the body down, from right here down. And we actually have to stop at where we're getting JPEGs and pictures and stuff, so we're going to have to scroll up a little bit until we can find the end of the HTML, because these packet captures put together all the packets that went back and forth, and after the GET for the main page, there was a GET issued by Firefox for the Twitter icon down here and the other icons that are on the page. So we want to stop at the HTML. And of course this is going to result in us having a page that doesn't actually have the images in it, but this is just a demonstration exercise to get the point of putting the protocols back together. We're going to copy that. And another way to open gedit is to go to Applications, Accessories, and gedit. Paste, and we're going to save this as tilde.html. Alt F4 to close, Alt F4 to close, Alt F4 to close. And we can do a Firefox on that Matilde file. And we can see, we can essentially play like in a browser, just the HTML payload of the TCP packets captured. And of course it doesn't actually look like the real page because we didn't include any of the pictures, and we would have needed to take some of those dots that were added in as tabbing spaces out of the captured packets. But we can see the idea of capturing TCP packets and other kinds of packets like ICMPs, and also the inner payloads like the HTML in these examples using TCPDump. And TCPDump is a great program for capturing packets and then Also being able to put them into a format that's exportable, the PCAP, that can be used in other tools such as Wireshark.